This conference will now be recorded.
Okay, good afternoon, students. In this class, we are going to derive that transmission loss formula. That is continuation where we stopped in yesterday class. So, I hope you are all written that formulas, equations. If you wrote means it will easy to understand you. I will note down that equations. Do you have any difficulty to understand that derivation? So why I'm asking means in that if you observe the derivation, each and every equation, uh, it is not related to the previous one. So if you practice more than 2 times, then only you can understand that in which step what is the form equation will come. Right, from equation 8 we will continue in today's class. Right, I'm going to start that class now. That is I'm saying. See, if you understand, if you practice and more than 2 times, means you can get that. So from which step the equation will come, like that you can understand that. So this is the equation we derived in last class up to 20. So this is the equation 8 here, and here we are considering that ng number of generators and nd number of loads. So based on this generation loads combination, we append this equation. So this part is belongs to the generator and this part is belongs to the loads. If we expand this equation by substituting ILK is equals to, so we have the equation, right? LK is equals to, say, I will show you that equation, right? So this is the equation 16 what we substitute in previous last one. So this from this equation I substitute this one in here. Instead of ILK, I substituted LK into ID. Now our aim is we have to find a total load current. So how much of current is required to minimum after the losses will be happening. లాసెస్ అక్కైన తర్వాత ఎంత లోడ్ కరెంట్ మనం డెలివర్ చేయాలనేది దీనిపైన డిపెండెంట్ అది. సో బేస్డ్ ఆన్ ద దిస్ కరెంట్ ద లోడ్ షుడ్ సాటిస్ఫై ద వాట్ ఈస్ ఇట్ రిక్వైర్డ్. సో అవర్ ఎయిమ్ is we have to find the total load current in the transmission losses. So from this if I take the ID remaining this term I can consider as a T. So T is nothing but this is the value we can get the value that is a symmetrical impedance value at kth bus. So that's why I'm assuming a letter is called T. So T is equals to Z1K into LK. So up to this we discussed in last class. Now the continuation of this class is today, sir. And here initially I'm assuming that I0 is defined as the current from bus 1 with all other currents should be 0. So ఇక్కడ ఏంటంటే I am considering I0 is a current that was sent to the bus and remaining all load currents IL I am assuming that 0. And why here the negative sign indicates means after finding the total voltages we had to subtract this value. So that's why I indicated minus here. Suppose we have the values V is equals to V1 plus V2 plus V3 plus so on. So these are the number of buses, but in that I am assuming only bus 1. So in that bus 1 if you want to find this value, then you can after that remaining will get Well, subtracting this value from this equation. So that's why I'm indicating minus here. Now, from this equation, V1 is equals to I naught Z1. So this one equation substitute in 19th equation. So this is the 19th equation. V1 is equals to summation of Z1I Ig1 plus. So our final requirement is we have to find the ID. So from this equation 19, we have to all converts into form of. So we are talking about only currents and impedance values, right? But here we have the voltage value. So we should have to convert this value into current and impedance value. So if you substitute here, then you will get minus I naught Z1. From this, how we can find the IDT? That is the intention here. So I will tell you how it will be become after this equation. So IDT can be written as, so this term will comes to this side, then you will get minus of summation and the entire term minus of I naught Z1. So our aim is we have to find the ID, right? So ID is equals to 1 by T summation of this one and 1 by T this one. Okay, now just note down these three equations. So after completion of jet test, tell me that. Have you all noted these equations up to here? Right. See, from this equation, we have to derive that ID equation. That is a total load current. Now, this equation, for applying the ID, so for ID value, we have to solve the previous. That is equation 21. We have to solve like this. So finally, we got that ID is equal to 1 by T summation of this one. And here, what we have to do means, so this is the total load current, right? Now, this total load current is by using this total load current, we have to find that what is the current with respect to the generators and the loads. That is ILK. That is the losses occurred in the kth bus. Why? Because we are assumed that we did the problem by considering that one of the bus that is called kth bus. So the current losses occur in the kth bus is given by LK into ID. Now from this equation, just substitute 22 equation here. Now the equation is become like this: ILK, that is the loss of current at kth bus, is equals to loss LK divided by T. So this all equation will get. Finally, the minus LK by T. So this is term we have, right? And this term can be written as rho K. Rho K is a constant value, and this value should be depends on that based on the performance criteria. It means the capacity of a plant. Suppose some plant generate that, so that is a maximum demand. So based on that plant capacity, we can decide this value, that is rho K. So reference, this is the equation 34. So after substituting that rho K in equation 3, what you will get? So this is the final equation, that is the last current at kth bus. And sometimes you will get two marks question. Write down the transmission loss formula. So you can write this formula. ILK is equals to rho K summation of 1 to Ng Z1I IGI plus rho K Z11 I naught. So this is the formula is called as transmission loss formula at kth bus. Now, after finding this losses for different buses at kth bus, at K or whatever it may be, so how many buses we have? We can find that all current losses at a particular bus. After that, we have to again update that generating currents by using this formation. So this is the generator bus, we have to update that, and this is the value how much of we have to update the current. So suppose previously let's consider it is a 5 amps. So due to the losses, it is reduced to 3. So what we have to do means again we have to update to the for 2, we had additionally we had to add 2. So that is given by this I new bus. Here this is the bus is give the information how much of current is required by the load from the generating station. So this is the updating value, that is new value. By using this value, we can update that what we have to generate from the current from the generating stations to the load with respect to the load. And these factors are called as coefficient factors, and this is given by that the parameters are involving in the transmission line in the form of impedances. See, up to here there is no deviation. So because this matrix is belongs to the generating station, right? So for generation, there is no parameters or so they can easily generate what is required. But when it is comes to the transmission line, there are certain parameters are involving like impedance values. Based on that, we have to update the value by using this parameter. So that's why the matrix form including that up to up to this part it is belongs to the generation. After this is it is belongs to the transmission lines. And the parameters have to be changed in the transmission line. That's why these all terms are including here. So here it is the term. It is row 1 Z11, row 1 Z12, row 1 Z1NG, row 1 ZLL. Similarly, row 2 up to row K. So finally, this matrix equation, if we can write in the form of I bar is equal to C into I nu. So here the C matrix is giving the information about what are the parameters are involving in the generating as well as transmission system. Are you completed? What about others? See, after assuming this matrix equation, in this equation we can update that all currents which is related to the generators as well as loads. Now, we have to show this equations row 1 z11 row 1 z12. These are all called as the B coefficients, right? Where we hear B coefficients, where we hear B coefficients. B coefficients అనే వర్డ్ ఎక్కడ విన్నారండి? So here the matrix should be converted into simplest form, that is I bus is equal to C into I nu, and this is represented as the 27th equation. Now if you substitute 27th equation 13th equation, so instead of this, so I bus is equal to C I nu, right? So instead of I bus I can substitute here C into I bus. So in this place, so this is the equation is belongs to the 13th equation. In this equation I'm substituting the 21, that is instead of I bus is equals to C into I nu. So this was I was substituted here, and PL is equals to, if you apply the transpose for both terms, you will get I transpose nu C transpose or bus C conjugate I nu conjugate. So this is the equation we can apply. This is the equation is called as power loss equation, transmission power loss equation. And from this equation, this is the power loss equation, and we have the complex power that is generated by the generator, and it is generated by SGA. So SGA can be, so starting we derive this equation. SGA is equals to VI conjugate into IGA, right? So in this condition, if you want to find the generating station 1 current, you have to use this formula. So IGI is equal to S conjugate VI sub. So here conjugate in the sense, actually the SGI can be written as PI plus JQI. If you are applying the conjugate here, the positive sign becomes negative. From this equation, you can write 1 minus JQG by, so this is called as a penalty factor that is given by the pi. So this is the formula for penalty factor for the particular generating station. So if it is the generating station 1, you can use that penalty factor. By using penalty factor, you can find that what is the current is generated by, what is the current coming from the generator 1. Similarly, generator 2, like that you can get it. Otherwise, if you want to find the penalty factor, you can find this PG1 and IG1. Then you can find that what is the penalty factor of the particular plant. So this is the equation we are using for finding the penalty factor. And we have one. So how we can calculate QG1 and QG2 means they will give in question itself the power generated by the plant 1 is 0.5 plus J 2 like that. So in that condition you can use that instead of QGI 3, instead of PGI 0.5. And one more thing, VI can be they will give in the form of in vector form, that is 1 plus J5 like that. So if we are applying the conjugate here, you will get 1 minus J5. So after finding these two values, then you will get that penalty factor of a particular plant. After finding this penalty factor, and we have the power generation, that is real power. By using these two values, we can find out what is the current from the generator 1. Just note down these equations.
ఏది జరిగినా మన మంచికే.
Are you completed, guys? Up to 13th equation. Right. So this is the penalty factor is used to find that what is the current from the generating particular generating station 1, 2 like that. Now, if you want to find the number of stations with using penalty factor in the form of matrix form, you can use like this. So I am using this. This is the equation for only single bus. If you want to find the number of buses, you have to represent this equation 29 in the form of matrix, and it should be shown like this. Just note down this equation, and this is the equation I am writing by expanding this equation. That is IGI equals to psi I PGI. So this equation I'm written like a matrix form like this. See, the above equation can be written as like 31 things. So I knew is equals to psi into PJ. So this is PJ, not PJ1. Represented it is equation 31. So it is PG1, PG2, PGNG, and so on. 1. And here the last column, the last row is called as a fictitious value. So what is the use of fictitious value in the transmission and power system is, see, it is used for the only for solving purposes, but we are not including in the real time application. So the fictitious value is only for analysis purpose. So why? Because this type of all parameters we have to represent in the form of algorithm. So while we are while designing the algorithm, we have to balance in the equations. If the equation is not balanced, the system should not work properly. It won't give the accurate results. Next. So now this is the equation 31. Substitute in 38. So this is the 38 equation, right? So instead of I knew is equals to, you can substitute here. So in this place, you can substitute Pi, that one. So you will get like this. So substitute equation 31 and 38. Instead of I knew equals to psi PJ. So this is PJ. Now while applying the transposition on both sides, that is 2 terms, then you will get like this. And in this equation 32, this term is calculated by using that RH criteria. See, RH, if you see RH criteria, if you see the means, so if you have one doubt, so how we can find that RH criteria in this, including in this equation means, so generally every generating station should be represented in the form of closed loop system, right? Block diagram. From this block diagram, if you analyze this all parameters, including this diagram, then finally you can find that one transfer function. From the transfer function, we can use by using the transfer function, we can finalize that characteristic equation. By using characteristic equation, we can stabilize that whether this equation is stable or not. See, if it is not stable, we have to update this value. So that's why it is denoted by RH, R of H. So here I am just simply writing that if any parameter is symmetrical, then both conjugate and its real value both are equal. So that's why I am simply written like this. So for showing that if the any one of the parameter is symmetrical, you can append like this. You can assume like this. Now this term is used for finding the B coefficients what we discussed in the transmission loss included for optimum scheduling, and this equation 34 is used for the finding the B coefficients. So we have different types of B coefficients. One is that is BII, BIJ, BJI, and B00. So these are the different types of B coefficients we have included in the power loss equation. See, if you want to find the power loss equation, you need this type of parameters. So that is the reason we are going to find this all B coefficient parameters by using this equation 34. So how we can find means this equation we can write in the matrix form. Let me see how it will be. Right. So here the previous equation, that is R of H is equal to, is there, right? So this equation while solving that, we can find that all B coefficients like this. So this methodology is for is a trial and error method. So why I'm saying parent method means you can't able to get that exact value at a first attempt. So we have to keep on going to change. So that's why this type of problems they are stabilized that and they are solving in the computer analyzed techniques, right? How it will possible means, so there are certain algorithm steps how we can solve this type of parameters, how we can solve this type of losses by using a computer algorithm. So there is a one topic you have remaining in the first unit, that is computational algorithm for optimal scheduling. So this is the topic we are going to discuss in tomorrow class. Then you can get idea. So if you want to scheduling this generating sessions, how we can approach in computational way. So what are the parameters? What are the steps we have? What is the step-by-step formulas we have to use in that? So that is the case we are going to discuss in tomorrow class. So just note on this equation. After this, we just observe the 33th equation. So the 33 equation is PL is equals to P transpose G1 R of H P conjugate G1. So if the this equation, if you write this in matrix form, so already you know that R of H, right? So if you write it in matrix form, we will get like this. That is 37th question equation. So right part we have only few minutes remaining. Students, have you all not done this? Are you completed up to 37th equation? That's 38. Right. Now, what are the different types of B coefficient? That is, here we have the B coefficient, right, in the matrix. So how we can indicate in the different form, and what are the units of this B coefficients in the power loss equation that we see in the next slide. So these are the different types of B coefficient is obtained based on the generation per unit. So why it is called means based on generation. Why it is called based on generation means generally if you in a present scenario there is a two three plants are connected together and they are combinedly scheduling that load demand. Why? Because a single plant is not proper way for delivering the load to load. So if there is any damage, if there is any damage occurring in the particular plant, it is not conveyed to the, it is not possible to deliver the load. So that's why there are certain conditions. Two three plants are connected together and they are scheduling that based on the demand and based on the availability of fuel. In that condition, the B coefficient should be changed based on the what type of generation is we are using them. Suppose some areas they are different thermal power plant and hydro power plant both are combined together. In some other plants hydro power plant and nuclear power plant. So based on this generation capacity, the B coefficient should be changes. Here these are the B coefficients when we have to convert from per unit to normal value. So per unit value to actual value, this is the way of we have to convert. So this is the actual value. If they give the per unit, so already we did the problem in yesterday class. If the given power loss equation in MVU, so here if the power loss equation they are given in per unit value, and this how we can convert this per unit to the megawatt by dividing this per unit value by 100. So here the SB is given by that MVA value. Okay. So by using this per unit by MVA, then you will get that actual value in terms of megawatts. And in this case, both are equal, per unit value and real value. And this is case we have to multiply with MVA. So these are the three coefficients we are using in the power loss equation. And here SB is called as base MVA. So just note down these three equations, and based on this you will get 2 marks question from this. So what are the different B coefficients we are using the power loss equation? So you have to write these three, and you have to mention this sentence also. The coefficient is obtained based on the generation in per unit. When the generation is expressed in megawatt, the loss coefficients are. So these coefficients are expressed in megawatt. So how we can get the megawatt means while dividing the per unit value with respect to the base MVA, and here while multiplying that per unit value with respect to the base MVA, then you will get this type of three B coefficients. So this is about transmission loss formula, and we have only one topic is remaining, that is the computational approach of optimal scheduling. So after the topic, now we are going to discuss about previous question papers. What are the questions we are getting from the first unit, and how we can have to attend that question, and what are the different problems. Then we will solve that problems also, right? So today's class is this is about transmission loss formula. So we have only one topic here that we'll discuss in tomorrow class. So I think I'm going to end up this class. Are you all note on this three? So these three coefficients are very important while converting that per unit value into megawatts. Right. See, just practice this derivation 2-3 times, then only you can get that flow. Otherwise, you can't able to remember that all equations at a time. Right. Thank you. I'm going to end this class.